If you've made it through all the videos, congratulations. And if you aren't even in the class and made it through all the videos, double congratulations to you. I wanted to make one more video to wrap things up and show some of the highlights of the semester. We started off in Chapter 1 discussing the principle of mathematical induction, which is a technique that we can use to prove an infinite number of statements with a finite amount of work. Mathematical induction is used in virtually every area of mathematics, and so it's an important foundation to have. We compared it to knocking down a line of dominoes. If you knock the first one over, and each one is guaranteed to knock the next one over, then all the dominoes will fall down. Chapter 2 discussed divisibility and the Euclidean algorithm. In this chapter, we saw how to determine whether linear Diophantine equations had solutions, and we also used the Euclidean algorithm to find them when they did. We also looked at the fundamental theorem of arithmetic, which tells us that all natural numbers greater than 1 have unique prime factorizations. In Chapter 3, we looked at some combinatorial proofs for number-theoretic statements. These are proofs that proceeded by counting numbers of objects in certain ways. We used these techniques to prove two important theorems in number theory, Fermat's Little Theorem and Wilson's Theorem. Chapter 4 introduced congruences. This is a way of reducing the integers down to a finite collection of objects that still follow some of our basic arithmetic ideas. We also introduced the Euler-Phi function, which counts up the numbers less than n that are relatively prime to n. This function found its way into several future sections. Chapter 5 took a deeper dive into working with congruences. We reproved Fermat's Little Theorem and Wilson's Theorem using a more number-theoretic approach. We also proved the Chinese remainder theorem, which tells us when we can solve multiple congruences at the same time. Chapter 6 was all about arithmetic functions, which are functions defined on the natural numbers. We learned about a special class of multiplicative arithmetic functions and saw how the Mobius inversion formula creates a type of pairing for these functions. In the process, we saw how we can construct the factors of an integer by breaking it into relatively prime pieces and working with them separately before bringing them back together. This turned out to be a helpful strategy in our proofs. Chapter 7 gave us a look into some of the ideas that are usually seen in abstract algebra. We looked at the orders of elements modulo m and proved that there always exists primitive roots modulo p when p is prime. In Chapter 8, we took a very quick glimpse at the prime counting function and the prime number theorem, but we couldn't go deep into that because we required some tools that we don't have at this level. You rarely see this type of analytic number theory unless you get to graduate school in math. Chapter 9 was all about the law of quadratic reciprocity. This is a way of being able to determine when the quadratic congruence x squared congruent to a mod p has a solution. It's one of the deeper results in number theory that has generated a huge amount of new mathematical ideas. Chapter 10 was a chapter that was really quite difficult. We looked at consecutive pairs and triples of quadratic residues modulo p, and in the process we looked at some fairly advanced techniques for working with sums of quadratic residues. The big finale here is that we proved that every 1 modulo 4 prime can be written as the sum of two squares, and we even had an explicit formula for it. Chapter 11 looked at sums of two squares and sums of four squares. These are two very classical problems in number theory, and in the proof of the sum of four squares we introduced the method of descent. Then we jumped ahead to Chapter 15, which gave us a glimpse at how we can use simple geometry to give us number theory facts. Specifically, we learned how to count lattice points in the plane using various techniques. In so doing, we are able to get estimates on the number of ways that we can write numbers as the sum of two squares, as well as the number of divisors the natural number n has. And this brings us to the end of the book and to the end of the class. I hope you enjoyed the videos, and I hope you learned a few things about number theory.